AERO2360. This is Aerospace Propulsion. We are presenting to you today our hydrogen turbofan research project, presented to you by myself, Kanchana Pulaj, and also Mark Wakefield. Our contents of this report will include our inputs and our assumptions, a spreadsheet model that is graphically introduced, also some technical modifications, ending with a conclusion.
Our inputs include ratio of specific heats, which is 1.4, Mach number, which is 0.85, cruise speed of 258 meters per second, ambient air temperature of 217 Kelvin, ambient air pressure of 23,630 pascals, bypass ratio of 10, a temperature ratio for the fan of 1.14, a temperature ratio for the compressor of 2.91, and for the combustor 1.82. The pressure ratio for the fan is 1.54, lift to drag ratio is 18, LH2 density is 70.85 kilograms per cubic meter, the kerosene density is 810 kilograms per cubic meter, the pressure ratio for the compressor is 32.48, and for the combustor is 0.99. Heating value for kerosene is 45 megajoules per kilogram, and for hydrogen is at 120 megajoules per kilogram. Specific heat at constant pressure we assume to be 1,000 joules per kilogram Kelvin. Our assumptions include the gravity at 9.81 meters per second squared, a range of 600 kilometers, maximum weight for the aircraft was 79 tons. Now, the aircraft will be flying within the stratosphere, so we assume that, and we assumed, therefore, we could assume a pressure and hence calculate the pressure based off the ambient temperature. We also assumed the compressor efficiency of 91%, assumed a fan nozzle efficiency of 95%, and a fan efficiency of 93%, and an endurance of 9.5 hours. So the first two graphs that you see are the compression ratio versus the thrust-specific fuel consumption, and also the relationship for the fan pressure ratio. So on the left, you can see that for both kerosene and hydrogen, we have an inversely proportional relationship, and the same for the fan pressure ratio and thrust-specific fuel consumption is also an inversely proportional relationship. On the left-hand side, you can see that as compression ratio increases, thrust-specific fuel consumption decreases to a point where the gradient is 0, and at which point there'll be the lowest thrust-specific fuel consumption for both kerosene and hydrogen. You can see that kerosene generally has a much higher specific fuel consumption than hydrogen. Now, the way that we calculated all these values, first what we did is we calculated the fuel-to-air ratio. We then calculated the FT on MA ratio, and then from that we calculated thrust-specific fuel consumption. So then we got a range of values and figured out the relationship between those values and thrust-specific fuel consumption. So what I just explained also is for these two graphs here. So again, an inverse relationship between thrust-specific fuel consumption and inlet temperature. And again, as you can see, the thrust-specific fuel consumption for kerosene is much higher than hydrogen. Actually, in here, what you'll notice is that kerosene is actually underneath, so the graphs are actually very similar for thrust-specific fuel consumption and bypass ratio. Again, inverse proportional relationship. As you can see, as you decrease bypass ratio from 10, you get a very high thrust-specific ratio, so your efficiency decreases. But as you increase your bypass ratio, as you increase bypass ratio indefinitely, your thrust-specific ratio becomes a very low value to a point where the gradient is 0.
As for modifications, heat exchangers must be added to convert liquid hydrogen into a gaseous state. This will ensure that the temperature of liquid hydrogen in the fuel control system lies between 150 to 250 Kelvin, reducing thrust-specific fuel consumption. The cross-sectional area should also be modified, achieving a better engine matching. Some improvements include the addition of a choke nozzle to improve mass flow rate, a bigger engine that can also be added to the increase of airflow within the chamber, and a beluga fuel tank, which could also be beneficial as it provides an even fuel distribution. Some advantages of hydrogen include that it burns at a slower rate, increasing the thrust, therefore increasing its range. It also has no carbon dioxide emission, only water vapour. It's a good source of cooling motors and generators within the aircraft, and it is also has a great energy density, allowing a greater payload. It also costs much less than Jet A1 fuel. Some disadvantages include its high flammability, and of course its emission of water vapour, which may lead to the formation of clouds, potentially putting the pilot's vision at harm. This research project conveys that the accumulated results, within the accumulated result, it is evident that liquid hydrogen provides a much better fuel source than Jet A1 fuel. Thanks for listening.